This is my video for the final exam. First, I will explain how the system operates. So at the beginning, we have been advised that there is friction acting on the back wheel. Also, there is a normal reaction from the ground over the rear wheel, which is of 500 newtons. So since there is friction, we can assume there is movement on this wheel. So I will assume the movement on the wheel is to the front. So it creates a moment like this, which will force the friction to go up on the opposite side. So the friction and the normal force happen in the exact same place. Then we have been told that there is a force P on this pedal, which will force this to move and cause this moment. We have been given the diameters of the wheel, the diameters of this little hinge, tuerca, and also the diameter of this circle and this another hinge or tuerca. So first we do the free body diagram of the wheel, which has friction, the normal force, the momentum, and the force in X and in Y from the tuerca. You do some of moments, some of forces in X, some of forces in Y. So we can get the moment that is exerted here. Then we do the free body diagram of this piece. So I call it free body diagram of the tuerca. We have the diameter, the force of P, and the force that comes from this wheel. And also we have a force in X and in Y in the middle of the tuerca. So we do some of forces in X, some forces in Y, some of moments. Since the force P is applied over this pedal and it is fully vertical, it has not angle. The moment we do sum of moments, so we only include the force given by the back wheel and the force P, which give us P. Then we go to the sum of forces in X, in which we have forces in X, the force given by the back wheel, and here the force P of the pedal has an angle of 20 degrees because it is exerted like that. So after we have P, we take it here and it is giving the X force. In the sum of forces in Y, we do exactly the same and we get the force in Y. So I also try to do the free body diagram of this pedal only, but I really don't get any equation that was helpful. So in this part I finish the point 1, 2, and 3. Point 1, explain how the system operates. Point 2, provide overview of the steps to solve the exercise. And point 3, sketch and explain the free body diagrams. I will explain part 4, sketch and explain the free body diagram for the section you're analyzing. So, as we remember in the last step, we obtained Tx and Ty. So Tx, I will call it Ax, and Ty, I will call it Ay. And here we will do the free body diagram from the RR cut, which will include Ax and Ay. Since we know the pedal has an inclination of 20 degrees, it will be very difficult to do the cut with an inclination. So we have to turn it a little, so it will be more easy to solve the cut. So after we move the eje, we get AY like this and AX like this. Remember, there is 20 degrees here, so we need another AX and another AY, which will become AY prime and AX prime. So to obtain that, we will multiply by do the sum of forces in X and the sum of forces in Y, and multiply the cosine and sine in which it corresponds. So we get AX prime and AY prime. After that, we do another Fibonacci diagram of this part, but only with RY and RX. These forces are given by the reactions of AX and AY, and since we have reactions here and reactions here, we could say that this part is spinning freely. So we will need a moment to make this part stay in the same place and don't move. So after we put that moment, we do sum of moments in R in this point. So these two are gone, AY prime is gone, and it only is being left AX prime. So we multiply by AX prime by 20 millimeters, which is the piece of the cut here, which is what it measures. Then we will do the diagram of the cut. We will have RY in the y-axis, Rx on the x-axis, and the moment will be represented on the z-axis. And we represent the moment with two fletches. After that, we will do the allow. We will need this allow to do the bending moment. Since we don't have bending moment, if we don't have the area, we will despejar A, and in the bending area we will use, instead of bending, the moment. So we put this moment and we get area. After this area, we realize that the point A and B are the most affected by this. So we will get our total moment by the sum of axial moment and bending moment. So the sum of these two give us 141.93, and we have to remember this has to be smaller than the allow force. So we will have to increase a little bit the area, so it will give us a smaller number so it could do, so it could nos pueda completar esta ecuación que tiene que ser válida. After that, we will use the new area to solve all the equations, all the moments. And after we realize this is good, we will have to also verify by the Brun-Mises moment. So to verify it, you have to do the axial force to the square and the direct force to the square. We take the square root and we realize this is much smaller than the T low.